Well, guess what? I was right. There is one more video here in 7.2c. So now we're finding volumes not revolving necessarily, but using other sorts of shapes. And we call these areas of cross sections. So we find areas of cross sections and we just add up all those little areas. So besides rotating, like creating circles, we can also create figures by making other shapes like semicircles or triangles or squares or rectangles. What we have to do is we have to figure out what is the area formula that we want to use for this cross section. And here's a bunch of different area formulas that you should all know, like the rectangle is length times width, area is of a square is just the side squared, triangle is 1/2 base times height, semicircle is 1/2 the area of a circle, 1/2 pi r squared. The area of an equilateral triangle, this one might be new for some of you, √3/4 times the side squared. You can derive that if you really need to. We create area equations for each cross section in terms of x or y, whatever we want to integrate with respect to, and then we integrate along from a equal to b. All right, so here's some examples. Find the volume of the solid whose base is bounded by the graphs y equals x plus 2 and y equals x squared with specified cross sections taken perpendicular to the x-axis. So let's see if we can draw this first. So we've got, let's see, x plus 2 is shifted up 2 and looks something like that. So this is y equals x plus 2. And x squared is just our normal parabola opening up, something like that. So this is y equals x squared. All right, now what happens, so here's our x-axis, is we're making squares from this guy. So we're going straight up and down here, and then we're coming up, straight up at you, and making a square. All right, so the area of this squared is going to be this side squared. So the area is side squared. So the side here is the top curve minus the bottom curve. So it's going to be x minus 2 minus x squared squared. So that'd be the area of one square. And this one square would have a little width that we would call dx. And we'd make it into like a cube, basically. So now what we do is we integrate from wherever they cross back here to wherever they cross over here. So from A to B. So we find where they cross here. I think it's out negative. I think it's -1, 1. So if I plug in -1, I get 1 for each of those. So yep, that's -1. And they also cross at 2. Right? If I plug in 2, 2 plus 2 is 4. 2 squared is 4. So they're going from -1 to 2. And this will be a volume, and it'll be of this whole thing that we just wrote up here, x minus 2 minus x squared, quantity squared, dx, like that. All right, so that is the formula for the volume, and if we want to find the actual volume, we can just throw it into our calculator, because again, I'm being lazy today. So math 9, we're going from -1 up to 2 along the x-axis. We've got this whole thing squared, so we've got, I don't even need the parentheses, the inside guy. We can just say x minus 2 minus x squared, close parentheses. That whole thing is being squared, and then we've got dx. And we get 20.1. So our volume here is 20.1. Neat, huh? All right, next up, we're taking this same shape here and we're making equilateral triangles from it. So we've got this exact same picture going on here. So there's our parabola, there's our line, and we've got, this is the base of our triangle, and we're coming out at you like that, making triangles. Where this is our side here. And the area for an equilateral triangle is √3/4 times the side squared. So it's going to be square root of 3/4, and the side here is going to be the same side, this length. So it's going to be x minus 2 minus x squared, quantity squared. So that's the area of the cross section. Now we want to add up all of these triangles, because like we're going to make a little triangle here that's going to come out at you. We're going to make a little triangle back here that's going to come out at you. Make a triangle here that's going to come out at you all the way along this curve. All right, so we're going to be integrating from -1 all the way up to 2 again. of root 3 over 4. And then we've got this exact same thing, x minus 2 minus x squared dx. So this 3 over 4 can, or root 3 over 4 can just come out front, and then we're left with essentially the same thing that we had here. So what we're going to get for our volume is that our volume is going to be root 3 over 4 times 20.1. All right, because this integral is going to be the exact same integral as this integral. All right. Next one, rectangles with heights double the base. All right, so the base is this, so now we're just going to go out twice as much. So we're going to have rectangles like that. So the area here is 2 times the side, or 2 times the side squared. And side squared is just the same thing we've had before, so it's going to be 2 times x minus 2 minus x squared quantity squared. So our integral is then going to be from -1 to 2 of 2 times this whole thing, x minus 2 minus x squared dx. In other words, the 2 can just come out front, and we're going to get double this answer. So 2 times 20.1 or 40.2. Right? Often these are related to each other because they are somewhat similar. Triangles with height equal to the base length. So now we're making triangles that have a height that is the same as this length. So the area formula for that triangle is going to be 1/2 s times s, right? Base times height, and they're both going to be s. So it's going to be 1/2 the side squared. Or in other words, 1/2 of that side that we've been using the whole time, x minus 2 minus x squared, quantity squared. So we get that our volume will be 1/2 the integral from -1 to 2 of that same integral we've had this whole time, x minus 2 minus x squared, quantity squared dx. So our volume is 1/2 20.1, which is 10.05. Neat how that worked. They were all kind of related to each other there. All right, let's try another one. One more here. So find the volume of the solid whose base is bounded by the graph y equals x and y equals x squared, with the specified cross-section taken perpendicular to the x-axis. All right, so let's take a look at this region here. So here's my x squared graph, and here's my, say, y equals x graph. And this is actually where they cross. Oops, I said y equals x. There we go. This is 1, 1. So I kind of blew this up as much as I could, and this was squared, not just squiggly too. There we go. And this, they cross down here at 0, 0. And we want perpendicular to the x-axis. So if we're doing semicircles, this would be the base of our semicircle, and then we'd come out around like that and make a half circle of it. So we got to know, what's the radius of this circle? Well, it's half the distance between them. So for number 1 here, the radius is 1/2 the top curve, which is x, minus the bottom curve, x minus x squared. And now the area of a semicircle is 1/2 pi r squared. So it's going to be 1/2 pi times 1/2 x minus x squared squared. So this is going to be 1/4 times this another 1/2. So we're going to have 1/8 or pi over 8 x minus x squared quantity squared. There's our area formula. Now we have this little width to it, and this little width to it would be a dx, because we're going to go along the x-axis here, all the way from 0 to 1, where they cross. So now we'd be integrating this. I'll put the pi over 8 out front. We'll go from 0 to 1, x minus x squared dx. All right, again, we can just throw that in our calculator if we want. Let's see, I'm going to have to move over here. There we go. Didn't want to go at first. So math 9 for integrate. And by the way, math 8 is taking the derivative. So from 0 to 1, and we've got x minus x squared, the quantity squared, and x was our variable, and that gives us 0.03. Let's get that as a fraction. So math 1, enter 1/30. So this equals pi over 8 times 1 over 30, or pi over, is that 240? Yeah, I think that's right. All right, next up, so that was number 1, semicircles. Number 2, squares. So now instead of that, instead of going halfway in the middle there, we're going to come out and we're going to do this as a square. And this is our side right here, and this is the other side right here. So for number 2 there, the area of a square is side squared, and the side is just the top one minus the bottom one. So our area is going to be x minus x squared squared. All right, so we're going to be integrating that. So we just integrate all those areas, and that's going to give us volume. And we're going to go from 0 to 1. We're basically making a bunch of tiny little rectangles that have a width of dx all the way, not rectangles, but squares, all the way along this guy. All right, so we're going from 0 to 1 of x minus x squared squared dx, which we've already worked out right here. It's 1 over 30. There it is. And then finally, the equilateral triangles. So now we're going to come out with a triangle. And remember the volume for, or sorry, not the volume, the area for an equilateral triangle is root 3 over 4 times the side squared. So we're going to get root 3 over 4 times x minus x squared squared. So if we integrate that to get the volume from 0 to 1, we're really just going to be pulling out the root 3 over 4, and the rest of it's going to be exactly the same. So we're going to get root 3 over 4 times 1 over 30. So 4 times 30 is 120, so we're going to get root 3 over 120 for our volume for the equilateral triangles. All right. So that is how we do cross sections. If you want, there's some pictures here in the homework that are much better with the cross sections, so you can see what cross sections are looking like here. A little bit better, but that is the homework coming up. Those are the homework questions. So that's the end of this section. So good luck. Go try the homework. We'll probably go over a lot of these answers in class.